Okay, guys, let's move on to our next, the practical portion of this, actually conducting the worksheets on this. So here I have two different variables from fictitious data from a motor learning lab, right? And it's depicted here on this first tab. And we're going to go through three different examples. The first thing I want you guys to do is there a correlation between these two variables? Now, there's a number of ways to do this, and I'm going to show you guys both of them. One being real easy, and another one being a little bit more advanced, but you get a little bit more information. So the first thing you're going to do is click on the Data tab, and all the way to the right, you'll see Data Analysis. And what it's going to do is going to bring up this dialog box, and what we want is correlation. Now, our input range is simply right here, and our data is grouped by rows, or I'm sorry, it's grouped by columns. So it's going to notify that. All we have to do is select our complete data set. We're going to click labels in first row, because in this row we have our labels. And now it's going to ask us, do we want our data to be put on a new worksheet, or do we want an output range? For this case, let's do an output range. And let's put it right there. And then I hit OK. And essentially it gives us a correlation. So you see it right now in this kind of grid format, and what it's doing, it's correlating reaction time with reaction time, and therefore we get a 1, because if I were to correlate reaction time with reaction time, obviously I'm going to get a perfect R value. Let me back up a little bit. Each one of these values is that R value, that lower, in this case it would be a lowercase r value. But if I were going to compare reaction time to as well as movement time, we get an R value of negative 0.3. That's very, very close to 0, meaning that, hey, if I move faster, it doesn't necessarily mean my complete movement time is going to be as fast as well. So in this case, the answer to the question is no. There is no correlation, or there is no association between my reaction time and my total movement time between these two variables. Now, what if I wanted to statistically figure this out? Well, unfortunately, when it comes to two variables or correlations, Excel will not do this, right, for two variables in the way we just did it. But there's a workaround for that. And the way we're going to do this now is I'm going to go back to click on Data Analysis. And if you scroll down a little bit, you'll see this thing as regression. Now, if you guys remember, regression, in this particular case, from Excel standpoint, regression is multiple regression. So I click on multiple regression, and let's choose movement time as our outcome variable, and our input variable, or our predictor variable will be reaction time. We have labels in our first row, and we want to know, remember what I told you about confidence level or confidence interval? We'll also calculate the confidence interval for that as well. And we want our output range. Let's put our output range right here. And one thing I like to do is I like to plot the line fit plots. And basically it just gives you a graph or scatter plot of our data. And it kind of helps you visually look at the data. So let's click OK. And as you can see, here is our data. Now, in this particular case, if you look right here, it's giving us the same value as right there. But in this case, it does not give us the negative value. And this is why it's very important for you to have, if you do it this way, to look at the actual scatter plot to kind of see if it's trending up or trending down. Typically, this will give it to you in some instances, but that's when we go into multiple regression. So as you can tell, there is no statistical significance. Is our correlation any different from 0? And our actual p-value to help us determine that would be listed right here, where it says significance f. Don't worry about what this means. F, that's gonna come way later when you guys progress in your statistical knowledge. If you notice here, that value is also the same value right there for reaction time. That's our predicted variable. And as you can tell, our p-value is the same, and there's no difference between the groups there. And we're going to talk about these values when we get on to regression. So that is the other way that you can do regression analysis or correlation with just 2 variables. So now let's move on to VO2 max. Okay. Let's say, for instance, you want to estimate an individual's VO2 max based off their mile walk / run in seconds. So you gather 18 individuals and you tell them, hey, I'm going to record your VO2 max as you run or walk this a mile, right? And I'm going to record your time. And as such, when you recorded those individuals' walk time, those who had the fastest, as indicated by lower in seconds, had higher VO2 maxes. So you have a good estimation, or you have good data to supply you with a way to estimate some of that data. And we're going to actually do that in a second. But the first thing we're going to do, as it says here in number 1, is we're going to calculate the mean, the standard deviation, and then we're also going to get the correlation coefficient between the 2 variables. We're going to do it the very simple way, as I described first. So let's go mean and then ST deviation. And if you guys remember our function, it's equal average. Highlight our column. And let's change this to a number so there's less significant places. And standard deviation is ST. And if we want ST deviation, and the S means sample, and that's what we want right there. And again, we're going to highlight our data. And that's our standard deviation. Now to get it for this easily, we just highlight those 2 cells, put our cursor on that little small box at the bottom of those 2 cells, and we drag it over. So now we have the mean and standard deviation for both of our variables right there. Now we want the correlation coefficient between the 2 variables. To do so, we're going to click on Data, Data Analysis, and Correlation. Hit OK. And where's our data? Well, our data is right here. We have labels in our first row, and it's grouped by columns. And let's pick a new output range right there and hit OK. So our correlation coefficient for this is a negative 0.339, which is a very high correlation. And the way you would describe that, or the way it would be shown in the scientific literature, would be R equals negative 0.94, meaning that the higher VO2 max that you had, the lower your mile, walk, run in seconds were. Okay. So the next question asks, what is the probability that the correlation coefficient occurred by chance? Why is the coefficient negative? Well, I've kind of just already answered that. As VO2 max goes up, you're able to perform your mile or your walk faster. But let's just do this real quick. I'm going to actually create a scatter plot. And to do so, I'm going to highlight this. And we're going to get into this in the next portion of the data analysis class. So if I highlight that particular data set and I go to Insert, and over here where it says Charts, you want to click on this bottom one with all these little dots in it, and it says Scatter. And we're going to click on this first one. And notice that it has this downward slope to it, meaning, if you guys can recall from the lecture, that downward slope is negative. Let's just clean this up a bit by taking these out. Another thing I'm going to do here is I'm going to actually add a trend line to this. And this trend line is particularly important because eventually we need to estimate somebody's VO2 max if they were to perform this in 540 seconds, as it says here in number 4. So if I put trend line, it actually gives me the line. But I also want to know the actual equation for that. Now the great thing about Excel, it actually does it for us. So you don't need to actually get these points and figure it out for yourself. So if you click on the arrow here and go to more options, this dialog box will open, and what we can do here is we can display the equation on the chart as well as display our R squared value. And let's just move this over, and I'm going to make it a little bit bigger, or maybe not. So that is our equation for our data set, and this is our actual R value. If I were going to take the square root of this value right here, we would get a 0.939. Now, the reason why this is wrong right here is because we only have 2 variables. So essentially this R would actually be a lowercase r, and it won't actually let me change that, but that would essentially be a lowercase r because there's only 2 variables. It's not an actual multiple regression. So that kind of handles a part of 4. So what is the slope and the y-intercept for the regression line? Well, we have it right here. Our slope is negative 0.726, and our y-intercept is 80.167. Therefore, if this were to continue, it'd go all the way to 80.1. Okay, so now we want to estimate a person's VO2 max for a person who runs 540 seconds. Well, let's just go ahead and do that, and I'll just do that through Excel. So our slope is negative 0.0726. That x value would be where I put in that 540, so 540 seconds, and I'll go ahead and put the intercept, the y-intercept right here. So the way we'll do this is equal this value multiplied by that value, and we're going to put parentheses around this. And if you guys remember to get that little asterisk, I hit Shift 8 and that's going to multiply. And now we want to add it, so we hit Shift, the plus button. We want to add the y-intercept to that. We hit Enter. And if somebody, if I was going to have somebody actually perform a VO2 max and they did it in 540 seconds, they would have a VO2 max of 40.93. And now let's just kind of look at that in the chart and where that would fall in. So if they did it in 540 seconds, which would probably be about right here, they would get it, they'd fall right in there. And that's, if you notice, that's not too far off from these values. So it's somewhere in that range. Remember, these are our actual values, and then this is the best line, right? So it's actually going to fit it on the line, but it's pretty close to where it would be. The reason why this is important to know is because in some instances, you're not going to have a way to actually calculate VO2 max, but you can use the associative time based off the data that we have to estimate it by simple regression equations. Now, it says here on number 2, I kind of skipped this. What is the probability that the correlation coefficient occurred by chance? Well, we don't know that, right? Because I did it in a way here where it doesn't actually give me that statistical test. But we're going to find that out right now. And it's going to go way back to what I just showed you guys from the first part. So we're going to click on Data, Data Analysis. We're going to scroll down to Regression. Let's get rid of this. So our Y range, let's just say that's our VO2 max. X. Let's put our output range right there. And let's hit OK. And notice that our scatter plots are very similar. The reason why I graphed it the way I did, actually let's do this. The reason why I graphed it the way I did is because if I do it this way versus this way, let me click on this and then go to trendline. It doesn't actually give me the option to put the formula there. It only gives me this. And in that case, nothing happened. Or actually, no, okay, so there it is. There it does. Okay, so never mind. It does allow us to do the same. So that's another way to do that if you want to get the equation in a simple way, right? By skipping, you can skip a couple of steps that way. Okay, but notice here that when I do multiple regression, it did not give me my my R value as a negative correlation. It gave it to me as a positive. That's why it's always good to have a visual representation of the data so you know which way to put the sign. That's very important. Here is our R squared value. Remember, that's the shared variance. So 88% of the VO2 max can be explained by this 1 mile runnable walk time. And is our correlation coefficient significant? Well, if we look at this value, that would be 0.123456789, or we just say 7. So yes, that number is less than 0.00, or I'm sorry, less than 0.05. So therefore, yes, our correlation is definitely different from 0. So if I were going to do this same exact test on 18 other individuals or another subset, I'm not going to expect that I'm going to get a very similar regression equation, or I'm sorry, correlation coefficient. And just to reiterate, that value is the same value as this right here. Just another way to find it. Okay, now let's go on to actually multiple regression. And I use this a lot when I was a coach. I use this particular type of data a lot because, again, it helps you narrow things down to where you can improve performance. And it's also very objective data that you can give coaches or even your clients or even your patients as to show them why you're doing specific things. So let's go ahead and figure out. Let's see, the first thing asks us, how well do our variables contribute to our model, right? So we want to see how body mass, squat, and deadlift, how well they correlate with sprint time. To do so, we're going to go to data analysis. We're going to go to regression. And let's go ahead and get rid of this. Our Y is going to be sprint. And then our predictor variables are going to be these. I'm going to just highlight all of them. They have labels, and we want a 95% confidence interval. Let's put our output range. Oops, messed that up. Our output range, let's go ahead and put it right there. And of course we want that. Let's hit OK. So let's just start by the visual representation. And it breaks it down into 3 plots. And let's just take a look at each one of these. So let's do this just to make it a little bit more noticeable. So let's make this enlarged so we get a better idea. And I'm going to change the axis. So obviously right here it says we have a positive correlation. And what that means is that as your body weight goes up, so does your sprint time, right? As your body weight goes up, so does your sprint time. And that kind of makes sense. Think of it in terms of, say, and I use this example all the time where I use football. Do linemen necessarily run as fast as running backs? Well, no, because they're obviously heavier. They have to overcome inertia. So that kind of makes sense where our correlation or our correlation would be positive in that sense. Now let's go ahead and look at, say, the squat exercise. And again, I'll kind of scale this to make it notice that we have a negative correlation here. And this kind of makes sense is that if we notice that if our squat goes up, our run time or our sprint time actually goes down. So the stronger you get, the faster you become. Now, why is deadlift, if we look at deadlift doesn't seem to have any association with sprint time. Well, one reason why that is because earlier I mentioned to you guys it's actually somewhat correlated with the squat. So the shared variance is being accounted for by the squat exercise. and therefore you're not going to have much of a correlation. And there it is, kind of laid out, and you can tell that there's no trend to that data, if that makes sense. So this goes up, this one goes down, and this one kind of goes along the line. And as we saw before, we can actually add a trend line to that. So you can see where things are going. But the first question asks us, how well do our variables contribute to our model? Well, the way we figure that out, and if you guys remember, in multiple regression, it's just from 0 to 1. 0 to 1. So we don't have to worry about negatives here. So in this particular case, these variables actually do contribute to sprint time. We do know that. And of those variables, they contribute to 97% of the common variance to sprint. That means that these three things contribute to 97% of the sprint. Keep in mind, this is hypothetical data. I made this data up. So there's obviously other things. What this would also tell us is that there's 3% of other things that you can manipulate to increase sprint time, right? But for the most part, we already have a good amount of the variables that actually contribute to a sprint. Now, here's where it becomes important for us to know. And it's these three things right here. And I'll highlight them. These coefficients help us to pinpoint where, I'll say this. It'll help us to pinpoint where our efforts can be made to increase sprint performance. To give you guys an example, let me write out this equation. It would be sprint is equal to, and our first slope, let's just say our first variable was, it's body mass. So it would be 0.029, all right, and I'm getting that value, that's our slope, I'm getting that value from right here. And that's going to be times body mass. Plus, the next one is squat, and our slope would be negative 0.009 plus our last one is negative 0.0002 times deadlift. Now, the way you can think of this is, let's say, for instance, I held each one of those things constant with an individual. Let's just say, for instance, this is, and I'm going to use one of our football players. Let's say this is Kavan, right? And I need to get Kavan's sprint time down. Which one of these variables would I want to target to get Kavan's sprint time down? Well, if I were to hold these two things constant, and let me backtrack a little bit. Body mass here, as you notice right here, I didn't put it, the actual, it's in kilogram, as is the squat, and as is the deadlift. And obviously sprint time is in seconds. So if I were to hold these things constant and I were to lower Kavan's body mass by minus 1 kilogram minus 1 kilogram, I'm going to be able to shave off 0.02 seconds off of Kavan's sprint time. Now imagine if I did that by, say, negative 10 kilograms. Essentially, I would lower Kavan's sprint time by almost a tenth of a second, which is rather large when we're talking about sprint performance. Now, if I were to couple that with squat, let's say, for instance, because this is negative, if I were to increase Kavan's squat by 1 kilogram, I'm able to take off I'm able to shave off 0.009 seconds off of his squat time. Again, that might not seem like a lot, but if I get him much more stronger and keep these variables constant, I can actually start making small adjustments to where they have big impacts. And if any of you guys watched the NFL Combine, you realize that those small details, anywhere from a 4.4 to a 4.5 or a 4.3 to 4.5, those are big numbers, and they definitely stand out. Now, same thing with deadlift. Deadlift doesn't have much of a contribution, but if I were to increase his deadlift by, say, 1 kilogram, I would lower his sprint time by 0.0002 seconds. Obviously, it's not a very big thing. So if I were, say, a coach prepping people for the combine, I would really target my efforts on body mass as well as squat. Now, you don't necessarily have to put them in that. You can always just look at the coefficient right here. And what I want to tell you guys is that you can also look at the p-values for each one of these coefficients to determine if they are actually indeed statistically significant, meaning that they did not occur by chance from a specific event. These definitely help contribute to that, whereas deadlift did not, right? But these two definitely did. Now, our coefficients, I gave us what we have, the lower and upper confidence intervals. Remember, like I said, there's nothing that's actually absolute. We actually have a range here. So our confidence interval, or I'm sorry, our coefficient, right, how much each one of those will contribute to sprint has a range, and that range is right here. It could be that I can actually shave off 0.04 seconds, or it could actually be 0.01. And as you notice, I'm 95% confident that this value would fall in between that range, right? But in any case, it gives a good determination to where I can target my efforts. And I hope that really helped explain its uses and how you guys might use this in your profession as you continue learning. Thank you.